proper and improper subsets. Proper and improper subsets. If we take a look on these two sets, let's say A is equal to A, B, C, and B is equal to A, B, C, and D. Then clearly from the definition of subset, A is a subset of B, because every element of A is a member of set B. For example, A belongs to B, B belongs to B, and C belongs to B. It means every element of set A is also an element of set B. But B contains at least one element. B contains D, which is not an element of A. D, which does not belong to A. That's why we can say that A is a proper subset of B. So we say A is a proper subset of B. When A is a proper subset of B, we can also say B is a superset of A, and we either write, it depends how you read it, we can write it as A is properly contained in B, or we can say B contains A. It's just like relation of father and son. If you talk about the son, you are going to say that A is a son of B. But if you talk about B, then you're going to say B is a father of A. So this relation of containing is really the way you read it or the way you write it. If you write first A, then A is a subset from reading from left to right. A is a subset of B, or you can say that B is a superset of A. So that is that's all about being a proper subset. We have also seen that every set is a subset of itself, but it is not a proper subset because there is no extra element. And next is power set. Power set. Okay, what is power set? Power set is a set of all subsets of a given set. For example, for example, if A is equal to 1, 2, 3, then set of all subsets of the set A is denoted by power set of A, and this now the subsets of A are going to be member of this set. So, well, first of all, let's start with the null set. Null set is a subset of every set. Doesn't matter whatever. So this is always going to be a member of the power set. So, and then singleton sets. Singleton sets are the sets containing only one element. And then 2, then 3, then 1, 2, then 1, 3, then 2, 3, and at the end we say 1, 2, 3, and let's put a bracket there because we want to close the set. So this is called the power set of A. If we count the number of elements 1, 2, 3, 4, 5, 6, 7, 8, there are total of 8 elements. If we really take a look, number of subsets is going to be always 2 power n, where n is number of elements in A, where n is number of elements in set A. So how many elements were there in A? There were 3 elements, so that's why number of subsets of A, or in other words, you can say order of power set of A is equal to 2 power 3, which is equal to 2 times 2 times 2, that is equal to 8. So that's how you can see that there are 8 elements in total in the power set. So just a quick question: if A is equal to 1, 2, 3, 4, then what would be the number of elements in power set of A? That's going to be 2 power 4. Yes, because there are 4 elements in the set A. So this is going to be equal to 16. 2 times 2 times 2 times 2. So this is how many subsets are there for a given set. Let's take a look on the next, and that is equal sets. So what do we mean by equal sets? Let's suppose that there are 2 elements, 2 sets. If there are 2 sets A and B, such that A is a subset of B, which essentially means that every element of set A is also an element of set B. Like all the elements of set A are also elements of set B. And also B is subset of A. Now if you take a look on these 2 relations, doesn't it mean that A is equal to B? Means every element of set A is element of set B, and every element of B in turn is also an element of set A. So essentially A and B both contain same elements. There might be difference in the order, but that we already know that doesn't matter. And there is another term which usually students may confuse with equal sets. That's equivalent sets. So if you talk about equivalent sets, the difference between equal sets and equivalent sets is that in equal sets, both sets essentially have the same elements or the same members. But in equivalent set, they don't need to have the same elements. A could be equal to 1, 2, 3, 4, and B could be equal to A, B, C, D. Now clearly you can see that A is not a subset of B, and same B is not subset of A. We can write it like this, that A is not contained in B and B is not contained in A. But there is clearly one thing that we can say, that number of elements in set A is equal to 4 and number of elements in set B is also equal to 4. So that's what where we say that two sets A and B are equivalent. So we say A and B are equivalent sets. So this difference should always be remembered, that in equal sets, both of the sets must have the same elements, but in equivalent sets, the number of elements in set A must be same as number of elements in set B. So now, just like we multiply numbers, we add ordinary numbers, we subtract numbers, we divide those numbers, but because sets are entirely different type of objects, so how can set operate on like what kind of operations we can perform on sets? So basically there are two operations which we can perform on sets. So let's talk about operations on sets. And these two concepts are key concepts, because ultimately when you learn statistics or boolean algebra or those kind of things like a higher level mathematics, these concepts are going to come handy when you will get to those branches of mathematics where we operate this way. So number one is union of sets. So if we want to define the union of two sets A and B is a set consisting of all the elements which are in set A or in set B. Union of two sets A and B is a set consisting of elements of set A, or remember there is a word or, and are elements of set So this, let's take an example. If A is equal to, okay, and this operation is denoted by this symbol. Don't confuse it with U. It's little wider than U. So if A is equal to, so let's take about example. If A is equal to A, B, C and B is equal to B, C, D, then A union B is going to be A, B. Now you can see that B is appearing twice. One time it appears in A, one time it appears in B. But if you remember the original definition of set, we emphasize that the elements of set have to be distinct. So by definition of set, we cannot repeat B. So that's why we are going to write A, B and C. C is also appearing twice, but in a set, because we have to keep all the elements distinct, so we cannot repeat C. We are going to write C only once. So this is A, B, C and D. So all the elements, if they are contained in A or they are contained in B, like we collect both the elements in set A and set B, and then we combine them and we make a new set which will be called A union B. Now there is another operation which is called intersection of sets. So the same way, if we keep talking about, so this time the intersection is intersection of two sets A and B is defined as a set consisting of common elements. Common elements in set A and set B. Notice that in union we use the word or, but in intersection we use the word and. So in this case, if we take two sets, let's say that we are using same sets A, B, C, and then we have another set B which is equal to B, C, D. Guess what? What is going to be intersection? A intersection is denoted by this symbol. A intersection B is equal to, well, A is in set A, but it doesn't belong to B, so that A cannot be included in the common elements. In intersection B, we are going to include only elements which are common to both. So definitely B and C are the only elements which are common to both. So this is what is called the intersection. In other words, we can say that these two sets A and B are non-exclusive because they have something common. And what are those common elements? Those are B and C, and that's what we call the intersection of two sets. So now we can also take a look on a couple of things. Notice one thing, is A union B is going to be the same as B union A. So because we also learned that the way you list those elements in set doesn't matter, you can write a set ABC, or you can write the same set as CBA. The order doesn't matter. So that's why A union B is same as B union A. And also, if for intersection, same thing, A intersection B is same as B intersection A. So this kind of relations are technically they are called this property wherever, and we are going to study this property again in when we talk about real numbers and in many other cases. This is this property where A union B and B union A, like the order doesn't matter. If the order of operation doesn't matter, then the property is called commutative property. Commutative property. And you can see that the union is commutative in sets, and also intersection is commutative as well. So this is a commutative property. Anyway, and next we are going to talk about the difference of two sets. So let's talk about the difference. Of sets. So suppose there are two sets by A minus B. We mean set of all those elements of A which are not in set B. So if you were to write this definition as B minus A, try now, and B minus A of course is going to be set of all those elements of B which are not in A. So if we take a look example, if we take an example of like A is equal to 2 3 4 5 2 3 4 5, and we take another set as B equal to 3 5 11 15 3 5 11 15, then what would be A minus B? And coming back to the definition, we say that A minus B is set of all those elements of A which are not member of set B. So 2 is not a member of B, 3 is a member of B, so we can't include that. 4, yes, because it's not a member of B, and 5 is definitely going to be there because 5 is not member of set B. So this is how you take the difference between two sets, or that's the difference of sets. And now universal set. What is a universal set? A set consisting of all the elements of the set under consideration is called the universal set. A set consisting of all the elements under consideration is called universal set. Okay, and now the next is complement of a set. Complement of a set. And what do we understand by complement of a set? So if U is a universal set, universal set is going to be the superset of all the is going to be superset of all the sets in the given question, and usually it's given that what is a universal set. If U is a universal set and A is a subset of U, if U is a universal set and A is a subset of U, then U minus A is called complement of set A, and is denoted by A complement. That's what you write. So A complement definitely is going to be A is equal to U minus A. Let's take a look at an example. If U is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10, and its subset A is equal to 1, 2, 3, 4, then by definition of difference of sets, what is A complement equal to? A complement is equal to U minus A, and this set is going to consist of those elements of U which are not in A. So definitely 1 is not going to be there, 2, 3, 4 are not going to be there. So what is going to be there is 5, 6, 7, 8, 9 and 10, because these elements belong to U but they are not in A. And interesting enough that if you take the union of A and A complement, this is going to be the universal set. And also one more thing that is worth noting is that A intersection A complement is a null set. There is nothing common between set A and the A complement. And then there is one-to-one correspondence. One-to-one correspondence. One-to-one correspondence. And a correspondence between two sets for each element of either set is paired with exactly one element of the other set. For example, if A is equal to 1, 2, 3, 4, 5 and B is another set, that is A, B, C, D and E, then we can establish one-to-one correspondence in such a way that one can be, when one is associated with A, we can make a pair and we can write it as 1A, or we can say that 2 is going to have correspondence with B, or we can write 2B. Similarly, 3 has correspondence with C, or we can write 3C, and 4 is going to have correspondence to D, or we can write 4D, and 5 has correspondence with E, or 5E. This is what is called correspondence. And this correspondence can be shown in many different ways. If we just use another method of developing this correspondence, let's say that we write 1, 2, 3, 4, 5 here as set A, and in set B we write A, B, C, D and E. We can establish this correspondence like by arrow headlines, and 4 has correspondence with D, 5 has correspondence with E. Now we arbitrarily are making these relations now, but later we are going to develop some rules. This association is going to be based on certain rules. And the next topic is disjoint sets. Disjoint sets. Obviously, two sets A and B are going to be disjoint, or you can also call them exclusive if there is nothing common between them. So, two sets A and B are called disjoints. Disjoints are exclusive if A intersection B is equal to 5. What it means that they have nothing common, and if they do have something common, then definitely they are not disjoint sets, and we call them overlapping sets. So let's continue on to an exercise, and these different concepts we have learned, we are going to practice them in an exercise, and let's call this as exercise 1.1. 1.1, and let's take a look on this question. Find two proper subsets of the following sets. Find two proper subsets. Subsets of the following sets. And let's say that the first set the first question is that I give you guys this set. So what are the proper subsets of this set? You can try it. I'm sure you can do it. So proper subset, how many proper subsets, how many subsets would be there anyways? So if you remember that formula, 2 power 2, there are going to be 4 subsets, but one of them is going to be improper. So there are 3 proper subsets and 1 improper subsets. The total number is 4, but I am asking only 2. Let's try it. So 1 is definitely going to be 1. The other is going to be 2, and another empty set is always the proper subset. So at least this does have. So just for your own practice, I'll give you a couple of questions, but I won't solve them. And try the second question, which is 1, 2, 3, and third question is A, B, and another question for practice is A, B, C, right? So let's do another question. Is there any set which does not have a proper subset? If so, which one? I repeat my question. Is there any set which does not have a proper subset? Wow. Which one is it? It's empty set. Empty set doesn't have any proper subset. It's only subset of itself, but you know every set is a subset of itself, but that is an improper subset. So definitely this question, the answer is the null set. Null set doesn't have any proper subset. So let's take another question, and that I'm going to say this is question number 3. Which sets possess only one proper subset? So which sets have only one proper subset? I know you guys are thinking about all those singleton sets. Every set which does have only one member has is a subset of itself, but that is going to be an improper subset. So and phi is going to be the only proper set subset. So let's take about 1. Okay. 3, 4, and 1, 2, 3, 1, 2, 3. Try some of these. Which sets have only one proper subset? Is your answer is going to be this one, or this one?